recording of the project given by the organization CureMD as a research aptitude test, in which I have to implement the paper by Fan et al. With the title Explainable AI using for the classification using probabilistic inference logic. So I'll be using Jupyter Notebook as an development environment, and Python as a language, and the framework, machine learning framework, will be scikit-learn. So first of all, I have imported all the required libraries which I will be using during the course of the completion of this project. So first of all, I have implemented the NumPy, which is a general purpose library used for the efficient mathematics calculation, and then the pandas library and the random library. So the pandas library will be used for the data handling, and then I have implemented different parts and models of the library from the framework of the scikit-learn, which will be directly used in the process of making models of machine learning throughout this project. So after that, I have imported some tools which will be used for during to interpret and make the functionality easy. After that, I have imported the matplotlib library, which will be used for the visualization of datasets, graphs, and their analysis. So from now on, we'll go to the dataset. So I have used the heart failure clinical records dataset from the Kaggle website. In this cell, I'll read the complete dataset file using the pandas library, and save it into the data frame of the pandas. So in this cell, the sum of the starting and sum of the ending and the sum of the last cells will be visible, in which we can see that there are 12 of total columns, whereas the death event has a binary output as 0 or 1 in the respect of all the 11 columns input. So here are age, anemia, and so on, the diabetes, where is the high blood pressure. So some of the columns, basically 5 columns, have binary inputs, whereas the other 6 columns have non-binary input. So due to the sake of simplicity, I will be changing these non-binary inputs to the binary input in the next step. So this is the complete information of the of our data set, where we can see that there are total 12 columns, and all are non-null. So there is no empty or sparseness in this data set, and these are the data types. All are the integer or float, all are the numeric data types. So for the sake of data pre-processing, we will be encoding non-binary columns to the binary columns as discussed before. So the binary columns count is 5, and the non-binary columns count is 1, 2, 3, 4, 5, 6, and 7. So all the seven columns values will be encoded to the binary input using the percentile values, where the values below the 5th percentile will be shifted to 0, and the values above the 50th percentile will be shifted to 1. So so we can see when we run this code, we get the percentile bounds, and then their encoded values as well. So the values after the, for example, the values after the 60 age of 60 will be shifted to 1, whereas below the age of 60 will be shifted to 0, and all other values of their respective columns will be shifted in the same manner. So we'll get now we will get the whole training data and the test data in the form of binary valued columns. So splitting up the data set, here we will split the data set for the as a targets, because in this data set the death event which is our target, which is the target column, or the in other word to say is the Y column. So we will split it in the Y data frame and the X data frame. So here we will be splitting. Here we will be coding this to achieve this splitting. So X is the data frame and dropping the death event column, and then the death event column will be saved in the Y data frame. So after splitting the whole data into X and Y, X like training and targets, we will further split up the data in the training data and training targets and the so similarly we will split up the X and Y split into the further split of train and test data, where there will be the X train split and the X test split, and the Y train split and the Y test split, which was done in using this line of code. And to remember that this split between the test and train data was done with the ratio of 80 as the train and the 20% as the test data. So we know that we have the 299 rows of the total data. When we will split the data with the ratio of 80 towards the training and the 20 towards the testing, so we will have the 239 rows for the training data and 60 rows for the testing data. From now on we will go towards building the models. So our first model will be a decision tree, where we will first build up the decision tree model, and later on we will train it. So this decision tree classifier will be taken from the scikit-learn library, and here we will be defining our model, and then we will fitting means that we will train our model using X train and Y train data. So after that we will score our decision tree, which will tell us we will score our decision tree on the X test and Y test data set, which will tell us that how much the accuracy we have achieved from our decision tree. So the accuracy of the decision tree after the training on the X train and X test set will result in the 56% only. After the training of decision tree, we will see that how good our decision tree can perform on the test data set. So for the sake of checking the performance of our decision tree model, we will use the score function from the scikit-learn and pass it to the test data as X test and Y test split. So from running this code, we will get the 0.5666 values, which represent that our decision tree has performed with the 56.66% of the accuracy, which is pretty low, and not as good as it should be. So furthermore, we will look further into the contributing factors of this much accuracy. So from this code we can see that the age, anemia, and the diabetes, like these were the four major contributing factors towards the accuracy. And like the time and smoking and the gender were the least contributing factors towards the classification. So then we made the random forest model. For this we use the random forest classifier from the scikit-learn, and then train it with the same data set which was given to the decision tree, which was the xtrain and the ytrain. So same data set was passed to the random forest, and then the score of the random forest was calculated in the same manner as the decision tree. So it turns out to be 0.66, which translates to 66.66% of the accuracy, which is around 10% more than the decision tree's accuracy. So if we look into the features which were contributing towards the random forest classifier accuracy, so it comes out to be that the age, anemia, so same contributing factors were also there, with a little bit of difference between their contribution. So here we can see that it has a little bit of balance between all the contributing factors than the decision tree model. After that, we have used the naive Bayes classifier. So we have built up the naive Bayes classifier using the Gaussian NB import from the scikit-learn, and then similarly train it on the xtrain and ytrain dataset. And after that, we calculated the accuracy of our naive Bayes classifier with the x-test and y-test dataset. So it turned out to be 73.33%, which is even higher than the random forest and the decision tree. In the last, we have made the neural network using the MLP classifier import from the sklearn. So our neural network has 4 layers of 16, 12, 8 and 2 layers per 2 neurons per layer, whereas the activation used in the middle layers are 10H, and the solver was used as the Adam, and the number of iterations were the 50. So why the number of iterations are so low for a neural network is because we have just 239 number of rows as the data. So if we put the number of iterations to a higher number, it will overfit on the data and start performing worse on the training data. So it was just put to the number 50. After the training of our MLP classifier, we have tested the accuracy of our MLP, which turned out to be 68.33%, which is a little bit lower to the naive Bayes classifier, but higher than the other two classifiers. This is lower, although neural network has a lot of capability to learn complex, most complex dataset, but here it has performed less than even a naive Bayes classifier, is because that the neural network does not perform well when the data is very limited or the very small on the very small data sets, because on the very small data sets are very simple, or like a decision tree or random forest classifier can even beat the neural network, whereas when the data is too high or too high dimensional, or the data is very high in numbers, then the neural networks start to perform well than the all other machine learning models. In the last, we will be modeling the model described in the paper, explainable AI for classification using using probabilistic inference logic. So for the sake of this model, we will combine the x and y split, which was done for the above 4 models. So it was concatenated, so the whole data was concatenated again in this cell, and then all the columns were saved for the later on use in this cell, and then we will come to this code after the next cell explanation. So in this cell, first of all, we will construct the knowledge base, which was given in the paper in the algorithm number 3, which says that you have to construct the knowledge base from the data, and then use that knowledge base as a training part. So in this function. We will be passing the whole data set to this function, whole data to this function, and then traversing each example one by one. So it will take the single row, and then from the single row it will take all of the columns and their respective values, and then the value of the last column, which will be saved as the label, and the feature values with their respective values will be saved in the feature value pair, and these feature value pairs will then be transferred to the power set function, which will be explained now. So this power set function will does is that it will take the feature value pair, and calculate all the possible sets of those feature value pairs for that particular row. So if we calculate mathematically that, then it comes to the end that this function will give us, because in the first we should know that we have 12 columns. So it will come out to be NC n 12 choose 1 to 12 choose 2 plus 12 choose 3 plus 12 choose 4 to at the end of 12 choose 12 combinations. So this power set will give us a total of 4095 combinations for a single row of the data set. So this K will be basically the combinations of 4095 combinations in total, which will receive as the power set here now. Then for the what will be done in the knowledge based construction function, that we will take the power set of each row and take the each subset one by one, and then calculate that if this set is already like saved in the count, because we will be now counting the occurrence combination of occurrence, because these combinations might happen in any other row of the data. So we will basically calculating here is the occurrences in all rows, and then count the labels against those occurrences, and then the ratio will be calculated here, and then the ratio will be calculated here against those clauses or subsets. After the calculation of power set for a single row, and we will see that for each of the combination in the power set, how much because this power the clauses in the power set of one row can also happen in the power set of any other row. So we will calculate the count of these clauses, and take only the unique clauses from the power set of all the rows, and also their respective labels as well. After that, when all the unique clauses from the whole data set has been counted, we will go through in this for loop. We will go through the labels ratio against each feature value combination, and thus in this way we will get to know that this particular clause will have the effect of this percent of the probability towards this label. So in this way we will happen to calculate the knowledge base, which will be used as the training of our current model. After that, we will construct KB direct function with our trained data, and we will also see that how much unique clauses we have constructed in the direct knowledge base, and also we will see one of the clause as well. So when we run our construct kb direct function, we see that the first row, this was printed for only the first row. So the first row has the diabetes value 0 pair and the anemia 0 pair, platelets with the 0 value, and the age value is 1, and so on. So these are total of the 12 values. These are the total of 12 values, and then 4095 basically depicts that the for just the one row we have received total of the 4095 combinations, and these 4095 will hold on for all of the other rows as well. And this is basically the total first five values of all the combinations we have calculated, which are 2,90,952, and this is the 100th clause probability pair, which says that the age is 1, diabetes is 0, and serum sodium is 0, and the probability is probability label ratio is 0.3488, and so on. So from now on we will construct the relevant knowledge base for the construction of relevant knowledge base, because the relevant knowledge base will be used for the test data. So before constructing the relevant knowledge base, we will use combine the split of X and Y test split, which was done for the models which was built before this model. So here we will be so in this cell we will be concatenating the X and Y test split, and we can see that we have concatenated all the columns here, all the 13 columns, with the last column which was basically the separated before. So similarly we will split the columns and save it in the test headers for the later use. After that we have defined the function to build the relevant knowledge base, and the reason for building the relevant knowledge base is that whenever the test query or the test row is passed to the model, if this part is not done, then it will have to compare with all of these 2,90,952 clauses. But if we build up the relevant KB, then it will come down to a couple of thousand clauses to compare only. So this was done, and this was given by the algorithm 5 in the respective paper. And what it does is that it takes the query. Basically this query is the row of it from the test data set, and this is the KB which was built in this cell, which has already been explained. So what this function will do is that it will take the row and make all of its feature value pairs, and then from its feature value pairs it will make the power. After that we have written the written the code for the construction of relevant KB, and the reason for the relevant KB is that because when the query row is passed to the dataset, then it has to compare with the original knowledge base, which required to be compared with all the clauses, which are 2,90,952, which is a huge computational task. Whereas the efficient way is to build up the relevant KB from the whole KB. Therefore, this algorithm number 5 from the paper by Fan et al. Says that you will get this single query, basically a single row from the data, and the whole KB which holds the whole 2,90,952 classes. And from this query we will calculate all the feature value pairs, and we will calculate all feature value pairs and then pass it on to the power set function, which was described here when we have constructed the knowledge based direct data set. So when this feature values of the query will be passed to the power set, it will give us the 4095 clauses of this query, which will be compared with all the 2,90,952 clauses of the original knowledge base, and only the common clauses of this power set and this knowledge base will be taken into the account and developed, and that will go into the relevant KB. So by doing this thing, the building of the relevant KB, we will dramatically scale down the size of the knowledge base for that respective query, which will be passed to this function. So we can see that when we will pass the test data to this query, and the knowledge base with all the 2,90,000 90,000 plus clauses, this will scale down the number of universal KB of 2,90,952 clauses to just only 3,943 clauses. So this will dramatically speed up the algorithm, and also computationally make the algorithm computationally efficient. From now on, we will solve the single query, this passed on single query using the linear programming techniques. And for that, for the linear programming, we will be importing further libraries, and here we will be using the pulp library, which was developed using the C and C++ for the language of for the usage in the Python language, and then from the pulp library we will be using the GLPK also. So as this project was the time constraint, so I have not implemented these two algorithms, the linear programming part and the algorithms number 6, which will basically explain the computation that why this query has selected this label or this label. So this will be done if the time will allow me, and it will be included in there as well. So for now, this is it. Thank you.